Hi, everybody. I'm here to ask this question to you all. How is the camera on your cell phone similar to detectors used to detect certain electron signals in a scanning electron microscope? Keep watching to find out. All right, we are talking still about scanning electron microscopy. We're talking about electron material interactions and more specifically the detectors. And I will, as promised, go over this slide several times. The kind of the different things you get when you hit a material with an electron beam. And one of the questions I get is, how come you don't care about melting with an SEM? You don't care about melting your sample for the most part. And well, the reason there is your beam current. Even though your accelerating voltage is the same order of magnitude as you would find in an XRD, the beam current is far less. It's multiple, maybe 3 orders of magnitude less than you would get on the X-ray generator in an XRD. So kind of remember that. You're accelerating your voltage to the same potential. So they actually have similar landing energies to that of the X-rays in an X-ray generator. I'm sorry, the electrons in an X-ray generator, but there's less of them. So current, it's a little bit different than V equals IR. I've said this before. But current means you have more electrons hitting the surface. So the beam current is about 3 orders of magnitude less than you have on an XRD. And the XRD, you're on the microamp range on a milliamp range. On a SEM, you're around the microamp range. Okay, so you're 10 to the negative 3. On an XRD, X-ray generator, you're 10 to the negative 6 in a scanning electron microscope. So remember that. Lower order of 3 orders of magnitude lower of the beam current on a SEM. That being said, you still have heat. We talked about the cold finger on the previous lecture on the S4800, where you can fill it up with liquid nitrogen to cool it off. And so heat is still a thing, but the signals we're interested in for this lecture are going to be backscatter electrons and secondary electrons, and we'll start taking a look at some characteristics of the imaging of these two. One thing I meant to probably put in that last lecture, so I'm going to squeeze it in here, is the terminology of working distance. And we've talked about working distance before when we talked about optical cameras. The working distance is, by definition, the distance between your final aperture and the specimen, so the height of the top of your specimen. And changing the working distance for the most part is focusing. However, you can set working distances at different points and then refocus. So it's a little confusing, but we're going to have a interactive lab, and hopefully that becomes a little bit more clear than just the words that are coming out of my mouth. When you're changing the focus, you're actually changing the objective lens current. And another thing I need to say is short working distance is needed for high mag. So if you have a really high working distance, like 15 millimeters or so, you're not really going to get high mag. On the S4800, you want a working distance of about 7 millimeters, thereabouts. And again, no absolutes, okay? Every sample is different, and you kind of have to play around with things depending on the sample you have. But working distance, again, in this case, it's the distance between the final aperture and the sample surface. So it's very much analogous to being the distance between the lens and your sample surface, okay, on an optical scope. Taking a look at some imaging here. So again, I'm using this article, and we'll see it again before the semester is done. I posted it because it's a pretty complete materials characterization exercise. And the one thing I'm going to kind of throw in here is this concept called edge effect. And if you have corners and even spherical objects, I'm using the example of spherical objects, you start getting this what's called an edge effect. And the reason why you're getting it is because you're getting a larger scatter of your secondary electrons, or getting a larger scatter of electrons. I'm kind of giving away a punchline here. If you have a sharp object, it'll kind of look brighter. It's not quite glowing, but it'll be brighter than the surrounding area. And that's because you're getting a higher secondary electron yield. And delta is generally used to signify electron yield. So on the circle, on a circle at the top of the circle, or sphere, excuse me, top of the sphere, you have less electrons being emitted in this surface relative to the edge. And the reason why you're actually getting more electron emission on the edges is because you actually have more surface area on the edge. And so you think of like a curve, you're getting the emission of the electrons from the edge. And the position of a secondary electron, if you remember, traditionally, they're kind of at the side, right? So you get these secondary electrons coming outside the surface, out of the side of the surface. And so you'll get that electron signal plus the electron signal from kind of the top going over there. And that's what this image here is trying to depict. So you have a higher intensity. And that is called edge effect. One thing, master of reusing recycling figures. Okay, so here's the part C for the image in this periodical. He had to have used this figure somewhere else because you can see the artifact. He left C in the figure, and not really trying to bash the guy. I actually respect him quite a bit. I actually kind of share his techniques for reusing his own figures in various periodicals. Anyway. Edge effect is an indicator that you're looking at a secondary electron image. So if you get an image like this, we don't have that informational bar that we have when the machine gives it to us, and the machine will usually tell you if the image is created by secondary or backscattered electrons. You can tell now, we're training you. You can train your eye to see what kind of electron signal made this image. This right on. This is a classical example of edge effect. Okay. Classical example of edge effect. So I know pretty 99.99% confidence that this is a secondary electron image. So again, edge effect. You don't see this with backscattered electrons. Why? Because something on the side isn't going to reach the backscatter detector, because that backscatter detector is always on top of the sample, because backscattered electrons go around the nucleus and come back out in an orthogonal direction. A secondary electron detector, I promised you I'd show you a schematic of the Everhart Thornley detector. This is a courtesy of Hitachi and kind of this little instructional book they give you when you buy a microscope. So you have your secondary electron, comes in this kind of weird vector, if you will. You have a scintillator, and scintillators are scintillating. I always used to say that's my favorite word. Maybe I shouldn't, I don't know. You have a scintillator, so a scintillator converts an electron signal to a photonic signal. You then have this photoelectric conversion phase, okay? So it's metal, right? So what's the photoelectric effect? You hit metal with light, and that light emits an electron. I'm sorry, that metal hits an electron. Okay, so the photoelectric effect, light hits metal, metal gives off electrons, and that electron is going to have an energy that's proportional to this photon. The energy of this photon is going to be proportional to the energy of the secondary electron. Okay, so you can have intensity controlled by kinetic energy of your electron as well. And that's how you get height detection. So if I have a lower Z surface, the energy by the time it hits this detector is actually going to be less than if it was right close to that detector. Okay, so that's how you kind of get depth of field type imaging. Well, anyway, you eject this electron, it hits this array of dinodes, which causes the cascading electron effect. So I'm amplifying the signal. Getting an electronic signal, you blow up that electronic signal relative to your scan area, to your screen, and that's how you have magnification in a SEM. 1920s technology, photomultiplier tube, really cool. I always like staring at this and imagining the electron signal getting amplified. Scintillator photomultiplier system. All right, so okay, scintillator here, photomultiplier here. You can have detectors that gather an electrons. I don't want to get in that. I'm sorry. Let's just talk about the scintillator photomultiplier system. Secondary electron detector, Everhart Thornley detector. In the previous lecture, I showed pictures of them. If you've forgotten what they look like, have a look at that previous lecture. On the other hand, we have backscatter electron imaging. I'm sorry, it's a little pixelated. I have the original somewhere, probably on a hard drive that I've used to back this stuff up. Here's an article myself and my group put out very recently, just last year. And we were putting solder and mixing it up with polymer, and we were drawing the solder in the wires. So we were doing a kind of an in situ wire drawn kind of material system. We did something similar with a tin fluorophosphate glass that we had made in the lab too. It's really, really cool. Some side notes. So you look at the different particle size distribution of the solder. This is a tin bismuth eutectic, and one thing that clues you in to the fact that this is a backscatter image is we see chemical related differences. So there's a tin rich phase and a bismuth rich phase, and if you want to figure out which is which, you can look at the periodic table. Okay. All right, so I have here my handy dandy periodic table. Hopefully you can see it on the camera. I'm going to try to get up, so if it doesn't come out, my disclaimer is I can't see myself. I can't see the little box of me when I'm recording these videos, and so sometimes I cut off the slides, and I'm sorry about that, but I've done my best to try not to. But anyway, tin, so it says for plated food cans on my child's periodic table, and then bismuth used in fire sprinklers. I kind of didn't know that till I stared at this periodic table. And so tin is element number 50, so it has a Z number of 50. And compared to bismuth, which has a Z number of 83, bismuth is a bigger atom, so the backscattered electrons are going to have more kinetic energy when they come around the nucleus, okay? And so the brighter phase is the bismuth-rich phase. The darker phase is the tin phase. When I started jibber-jabbering about these spheres, I talked about particle distribution, and then I cut myself off. You see I have kind of big, these little satellite particles. This means that this solder, I call it solder, but this tin bismuth alloy, if you will, was formed by gas atomization. And if you had me for material energy balance, hopefully you remember the gas atomization problems we worked through. Really cool stuff. One thing you don't see, so let's go back and look at this one. This is a secondary image. We clearly see edge effect on these particles. These also have satellite spheroids, and so this material was also created by gas atomization. I don't rightly remember which one this was. It may be a steel one, but anyway, the ring around the sphere, if you will, is edge effect, so that tells us it is a secondary electron image. This one, no ring around the sphere. The contrast is purely driven by chemistry. That tells us this is a backscattered electron image. So kind of things that are important to know when you're looking at electron micrographs is what signal are you looking at? That helps you interpret the data. It's very, very important to know what signal caused which. And I have had several arguments with people basically telling me you cannot see holes or something like that on the scanning electron micrograph, like literally a hole. Like if I have a flat substrate has a hole in it, people have told me you can't discern it. That's incorrect. You have to know what signal's generating your image, and then you can determine if it's a hole or if it's just chemistry related in terms of contrast. Because remember, a lot of looking at micrographs, even colorized micrographs, okay, is still about looking at contrast. In this case, we're using literally the difference between black and white to discern things. Okay, so think of it that way. Difference in levels of black and white. This is the background. Um, Incidentally, this is a carbon dot. This black background here, carbon dot. It is the darkest signal on this micrograph. In carbon, I don't even have to look at the periodic table. It's 6. Much lower than, I have to come back, I forgot, 50 for tin and 83 for bismuth. Okay, so that explains your contrast mechanism on this backscattered electron image. Here is a head-to-head comparison, and I have my own head-to-head comparisons, but I still kind of use other people's imaging because sometimes they're actually really, really good. And it's hard to see. This is the secondary image. There is some edge effect on this secondary image if you really look closely. I'm trying to mouse it with the pointer. Here, purely contrast driven. A lot of times geological specimens are really, really cool to look at, particularly under backscatter electron imaging. And super cool, super nice. Anywho, let me go on here. This is from an article in a journal called Micron, and this is about technology put out by Zeiss. And it kind of mentioned different scanning electron microscope brands, and I don't know how I forgot Zeiss. They make very premium scanning electron microscopes. They've put a lot of engineering into where they put their detectors, and they even have an in-lens secondary electron detector. And you can tell, so B, it's the in-lens secondary image. Again, their premise is that the chamber of the SEM is like a fireplace, and that most of the signal goes through the chimney, just like most of the heat in a fireplace goes through the chimney. So that's a lot of the principle behind Zeiss design. And here's a below lens SE detector, and if you notice, they're kind of depicting it at an angle, and this is analogous to what Hitachi has for their below lens secondary electron detector. Okay, and if you remember back on that 4800, they have a traditionally placed secondary detector kind of at the back side, but then they have that kind of higher one, which is designed to compete with Zeiss basically. And but you see, their premise is that the best is in lens. Okay, and so in lens SE, we get a lot of different information. And so sorry, this is a low loss backscatter image. So they're looking at chemical. And it's also important if you have a SEM with multiple detectors to look at images from the different detectors side by side, because you never know what information is going to jump out at you. So A, below lens SE image. So this is a secondary image. This B is the in-lens secondary image. And right away, we see a higher fidelity in terms of the detail, particularly here. Okay, so sometimes when you have topography, the electrons bump into your own specimen that are being emitted, so they don't quite make it to the detector, is kind of the analogy that's used here. What's interesting is that they're using this window on the same specimen to make a comparison. This is kind of classical. It shows kind of a classical problem that you run into with backscatter detectors. Okay, so this C is a low loss backscatter detector. Look at it very closely, even though maybe I'm talking a little fast, but look at it really closely and you see differences in surface feature. Okay, and this is the argument I get into people. So I can tell you from the secondary image that this part of the specimen is recessed. Okay, so this is analogous to the hole I was talking about. Argue with people all the time. You can't see holes with an SEM. Well, yeah, you can, but you have to know what signal you're looking at to determine if it's a hole or not. Okay, here it'd be really hard to really discern this as a depression or a hole in your specimen. With the secondary imaging, you get better topographical, or classically, historically, you've gotten better topographical type of information. So I can say pretty confidently this is lower than this, okay, relative to the same Z. Here, their in-lens detector, much more higher fidelity on the topography. And if I compare this part of the triangle to this part, I mean, I see facets that I don't resolve with a typical below lens SE detector. Okay, so this is the power of putting your detector in the lens. Okay, they have the in-column backscatter detector, or the low loss backscatter detector, and you get kind of chemical information here. I'm personally not dazzled by this. Okay, I'm more dazzled by the fidelity in the image they get from this in-lens secondary detector. So kudos for patenting this and making it so other companies can't really do it. But anyway, here is the difference head-to-head, different detectors, same exact type of imaging. In-lens detector giving you really incredible topography discernment, if you will. Again, just compare the facets here and here. These are both secondary images. How do I know if it didn't tell me? I was covering it with my hand. You can't see me covering it with my hand. The edge effect is a dead giveaway right there. Edge effect there, edge effect there. We see kind of edge effect there. We see some quasi kind of edge effect here. Okay, it's brighter because of the position of this crystal versus the detector, so it's kind of cool. Two flavors of standard, if you will. Standard for the rest of SEM manufacturers. You have this YAG scintillator. And so I told you on the 4800, they have this Robinson backscatter detector. And that Robinson backscatter detector is this YAG scintillator. So this yttrium aluminum garnet crystal scintillator. It then goes through a PMT. So it's very, very similar to our Everhart Thornley detector. But this is a Robinson detector. And I believe it was a woman named Vivian Robinson. You can Google it. Prove me wrong. It's either Vivian or Victoria. I'm pretty sure it's Vivian. Robinson backscatter detector, and that's what we have on our S4800, our field emission SEM. Back here, this is a field emission SEM, and we talked about guns in the previous lecture. So this would be the brightest gun. The detector that we have on both the tabletop TM1000, I've called it TM100 several times. It's a TM1000 tabletop SEM, and the SU3500 SEM is a so-called semiconductor detector. So both detectors have similarities. Okay, so both of them are placed exactly on top of your specimen. This is using a scintillator, which goes through this type of process like we saw here, goes through a scintillator to convert the electron to a photon, and then through the photoelectric effect on this photoelectric conversion phase back to an electron. Okay, this here, and I kind of started saying you can have systems that convert an electronic signal to an electronic signal. This is a semiconductor device, and it's very similar to the camera that's on your cell phone. Okay, so it's a CMOS image sensor like. Okay, very, very similar. This CMOS image sensor is detecting photons. It's using basically the fact that there's wave particle duality between photons and electrons. So a photon is a packet of energy. In this type of scenario, an electron's basically a packet of energy. Okay, and so it's kind of I guess more of the particle aspect of the wave particle duality. Very similar to the CMOS image sensor on your phone. And so that answers the question posed at the beginning of this lecture. Anyway, very similar, two different flavors. This is more desirable than this in a lot of cases. And I had a microscopy class where we actually did a head-to-head because I had it beat into me that these were only good for very smooth specimens, polished like a metallographic specimen. But we actually had a head-to-head comparison in a different class that I teach on electron microscopy and showed that we actually get good topographical information as well off of a YAG scintillator PMT-based backscatter detector. This is a diagram now. Their 4 quadrants, so 4 semiconducting quadrants on these semiconductor device like backscatter detectors, and you can change the biasing, and so you can change it to where some are positively or negatively charged, and that changes the imaging characteristics. These two are backscatter imaging, and this is a different type of detector called an ultra variable detector. It's actually proprietary to Hitachi, and you can see that you get slightly better topographical information off of a UVD detector. And that's because UVD detector, the image is analogous to a secondary electron detector. And I'll talk a little bit more about this. One thing, on a variable pressure SEM, you can actually bleed air into the system. And that means you can't actually use your Everhart Thornley detector. So you can't use a scintillator detector unless the vacuum is high. If you go to a low vacuum situation like we see on the TM1000, and we can set it on the 3500, you have to use digital detectors basically. And so you have to use this semiconductor type detector. And in the olden days, this was called an environmental microscope, basically, or an environmental SEM. Nowadays, we can put kind of non-conductive, or I did my air quotes too soon, wet specimens in a traditional SEM that has specialized detectors. UVD, and I'll have a diagram I'll share with you later, but verbally I'll tell you, you still make secondary electrons when you're bombarding your specimen with your electron beam, even if you're in low vacuum. If you remember, the energy of a secondary electron isn't as high as that of a backscattered electron. So the backscattered electron will still go through the air and hit your detector. The secondary electron, not as energetic, but it'll interact with the air and emit photons. And the photons emitted from the air have an energy level that's proportional to the secondary electron. So this UVD detector actually is detecting emitted photons. Since these photons have an energy level proportional to the secondary electron, you get secondary imaging, or imaging that's like secondary imaging. These are both backscattered electrons. This is BSE topo, this is BSE 3D. This BSE 3D is actually more sensitive to chemistry differences, and this is a shell I found that was dredged from the Rio Grande, and so this is on a shell, so it's pretty much calcium carbonate, so not exactly conductive. So it's actually pretty cool. This UVD detector, so I promised I would talk about it, and I will live up to my promise really, really soon, right? I just already went to that other detector. So this UVD detector now, this is operating with air in the chamber. BSE detector, you can bleed air into it. This backscattered electron will actually, the backscattered electron will actually hit the backscatter detector. You bleed air into the system to cut down on charging, and we haven't talked about charging yet. But charging is where you get extra electrons on the surface, and in this case, these extra electrons interact with the air, and positive ion originated from the gas molecule, so opposites attract. It'll interact with the air. So in this case, gas is air. Here with this UVD detector, the secondary electron, and that's what it's not a very good color coding. Blue on blue, not a very good color coding, but I got this from Hitachi. The secondary electron is depicted by this lighter blue electron. It interacts with the gas, and you excite the electrons in the gas to a level. They de-excite and emit a photon. That photon has an energy level proportional to the secondary electron, hits the UVD detector. You then get a image very similar to a secondary electron image because of the proportionality and energy. Here it's just different biasing. So BSE 3D, there's actually another extractor. Is it anode? Yes, an extractor anode here. And it's a little bit different than the anodes you find in the column, okay? And it's turned on and it gives you a perspective. And so it gives you topographical-like imaging. And you also see this with topo, which is code for topographical. So it's trying to give you a topographical-like imaging in topo mode. So 3D and topo mode. Again, electron-material interactions, they're elastic and inelastic and elastic phenomena. All right, so kind of recapping, we've seen figures that accompany this. And so signals uses, so secondary electron, we talked about that, surface topography, fractography, and failure analysis. Backscattered electron, atomic number contrast and phase contrast, although if any of you all took failure analysis, you probably used the tabletop TM1000, and that's purely a backscatter detector. Characteristic X-ray, so energy dispersive spectrometry, EDS, localized compositional analysis, and X-ray mapping, and we'll get to that. But first, I kind of wanted to explore a little bit more about the Zeiss work on low loss backscattered electron analysis, and it's a quasi-new technology. This gentleman, Heiner Jacques, and unfortunately he's passed away. Really smart guy, and I had the pleasure of meeting him. He's probably the closest to meeting someone that could win the Nobel Prize that I'll get to. And so it's pretty interesting. He kind of has a different graph in terms of energy. So this is secondary electrons. This is Auger electrons. And so slightly higher than the energy of a secondary electron. And we have these backscattered electrons. So we kind of talked about that. And so he has different categories of backscattered electrons. And backscattered electrons as a whole are actually low loss in terms of losing energy, right? Because they come around, they actually gain energy depending on what the chemistry is. But anyway, I kind of wanted to talk about it because he talks about different type of scattering electrons. And the Rutherford, so the primarily electrons we talk about in terms of backscattered electrons are referred to as Rutherford backscattering electrons. And there's this other flavor called channeling backscattered electrons, and they have more of an interaction with the crystal structure, okay? And so you have this kind of Bragg angle type of interaction. And I won't get into too much of the differences, but the point is it's a design of a detector with the realization that within this spectrum of backscattered electrons, there's different flavors, so to speak. And I talk about some fallacies I see in this more to try to help with your learning, and it's not necessarily meant to be a criticism of this work. And utmost respect for this gentleman. He's passed away, and also Zeiss as a company for trying to further the awesomeness of a scanning electron microscope. I'm really kind of into that. So there's a different flavor of these so-called low-loss backscattered electrons. We talked about the and I've missed a part. I need to kind of double back and talk about the scatter here. So I'm reminding myself right now, and I'm recording it so I don't forget. But you all get to see it, so sorry about that. Our typical backscattered electrons have a deeper scattering volume than these so-called low-loss backscatters, these Mott backscattered electrons. Okay, they are a smaller scattering volume, and thus make up a weaker signal, okay? And so you have to have a special detector for that. And Rutherford backscattering, this is what I'm talking about when we see chemical differences. We've seen this, and they're criticizing because they're trying to sell their Mott backscattering detector, okay? But it kind of says some stuff, right? It's saying you're getting too much signal. You're getting too much scattering, right? There's this kind of this spatial thing, that you get. And this is these three here are the same mag, same location, pretty close. Oh, they're not the same mag, are they? I always confuse myself because you actually do see different stuff with the MOT. And I question myself every time. No, they're pretty close to the same mag if they're not exactly the same mag, these three. So this is Rutherford backscattering imaging. Pretty much the images I've shown you back here, and I skipped this, and I need to get back to this. Back here with the solder or tin bismuth is Rutherford backscattering. You get good chemical discernment. Here, they're saying with their low loss imaging, you get more information from this MOT backscatter. And so you have Rutherford backscatter, you've combined the signal with Rutherford and MOT, and they're right on. They're saying you're getting Z contrast imaging here. This is a metallographically, no, it's an ion mill polished specimen, so it's super smooth. It's even smoother than what you get off of a metallography polishing wheel, unless, of course, you're Bradley. He's the smoothest of them all. Here, you combine your signal with the MOT, and you start seeing other details. And actually, they're saying it sharpens your image. Here you have a purely MOT backscattered image, and you start seeing, they're saying it's lattice information, okay? And I was in a seminar where this gentleman was first presenting this, and someone stood up and said, now, how do you know it's not an artifact of your ion mill? And he was right on in his answer, okay? These rasters are in different, or these linear features are in different orientations, so it can't be the same ion mill that's doing it. And so the assertion by Heiner Jacques from Zeiss was that this is lattice information. So you're actually getting some idea of even the crystal structure of your specimen using this MOT imaging. And this is a zoom in of this, okay, saying you're actually getting, he's saying surface information. So I don't know if this is a surface feature or if you're actually getting, and he didn't either, getting some information pertaining to the crystallographic orientation. So it's actually really cool. We'll talk about orientation imaging microscopy in the next lecture. So you can get crystallographic information. I've alluded to that before. It's the nature of a backscattered electron. It interacts with the lattice, so you can actually get diffraction patterns. Before I go too far, I skipped this and I apologize. So electron material interaction, the beam hits the surface. I've tried to depict the scattering area of different things, okay? So backscattered electrons are coming from below the surface, secondary a little bit closer. Auger, it's almost considered a surface. It actually is considered a surface characterization, so really close to the top. X-rays can come from even deeper, depending on this chain reaction of electrons that kind of go through the material. What you get is a Monte Carlo simulation. And then I have this picture I got from 267 in our book, and it's showing the relationship in scattering depth. And so A is, this is carbon, so it's better to compare carbon and carbon, but there's also a Z type of effect as well. So carbon is 6, a gold, I'm lucky I've not thrown out my child's periodic table. Gold is 79 on the periodic table, so element 6, element 79. And if you look at 15 kilovolts of accelerating potential on this beam, you have this area 1 micron, 1 micron. So if I kind of guess, maybe this is 2 microns of penetration. Here you have the similar scale bar, but it's denoted as 20. I've lowered the accelerating potential to 1 kilovolt, so I'm only getting 20 nanometers of penetration into the carbon. So only 20 nanometers of where the scattering's coming from, so even closer to the surface, right? This assumes the same accelerating potential, okay? Here we have a higher Z specimen, and we're back up to 15, so this is compared to this one, and we're roughly an order of magnitude less scatter in the higher Z element. So that's what's meant by Monte Carlo simulation. You don't exactly know where the electrons are going, so sometimes you don't exactly know where they're coming from. This error, if you will, only increases at a higher accelerating potential. So if you're able to, sometimes it's actually better to scan things at lower accelerating voltage. The maximum accelerating voltage on the 3500 is 30 kilovolts. And so people always want to amp it up. Two things: you'll kill your filament a lot quicker. Also, you might not be getting the spatial resolution you need, depending on what you're looking at. So back to this, I kind of took that little segue. Backscattered electrons, so this is traditional Rutherford versus low loss. You're getting much different contrast mechanisms, so the idea is you get more information. And again, all discerning differences in black and white. Okay, no colorized micrographs here, and colorized micrographs are actually fake color anyway, unless you're looking at an X-ray map. Okay, just throwing that out there. We'll talk about X-ray analysis here pretty soon. One thing that gets me is that the assertion by Zeiss was that these are dislocations, and there's no way that these are dislocations. They're too big to be dislocations. Two, you cannot see dislocations unless you're using a TEM. I'll just go out there and say it. So this is a little bit wrong. Always be careful when vendors try to tell you something. Okay, and I was in the semiconductor industry for some time. I used to evaluate microscopes basically for purchase, and so I worked for Intel. If we purchased a scope, we were probably buying 1,000 units. Okay, so it was always a big deal for vendors to try to sell to us. And one thing, and I'm not quite joking when I say this, they would show their marketing slides and they would show the same micrograph. And I was in the business for a little while, and I swear to you, I saw the same presentation multiple times, and they were just making that scale bar smaller. And so I tried to call them on it one time. I won't tell you which vendor. But anyway, they're saying these are dislocations. I have a hard time believing that these are dislocations. If you look at the scale bar 1 micron, and you consider that a definition of a dislocation is what? An extra or missing row of atoms at the highest level. I have a hard time saying that something on the scale of angstroms is going to be discernible at this visibility. So I think this is wrong. Again, they're showing they're saying this is dislocations again. The scale bar is even bigger, so I don't think this is correct in that they're saying these are dislocations. It's some other feature. I do not believe this is dislocations, and I'll show you when we start looking at TEM. Dislocations are very small. They're not on this order of magnification. So that's one thing. And again, no disrespect to Zeiss or Heiner Jacques. I just have to patently disagree that these are dislocations. So on that, this is a good place to end the lecture. And if you have any questions at all, feel free to email me. And again, thank you very much for your time.
Oh my. It's the end of the lecture. If you have any questions, you can email me at drobertson@utep.edu.